Hello everybody, today I'll be talking to you about the 1,4-diphenyl 1,3-butadiene that we will be doing in lab this week. You can also read Pavia Lab Manual, page 91. Before we begin, we'll go over a little bit of the safety information. Sodium ethoxide is a very strong base, so be careful when handling. It's corrosive and it will burn you if it gets on you. If there's any spills of sodium ethoxide or other chemicals, make sure to clean them up as soon as possible and dispose of the waste appropriately in either a liquid waste jug or a solid waste pail. If you have any questions of how to dispose of chemicals or how to clean up a spill, please ask your TAs. This experiment highlights the Wittig reaction, named after George Wittig, who won the Nobel Prize in Chemistry in 1979 for his work on this reaction. It's a very robust and versatile reaction capable of creating new carbon-carbon double bonds with a wide variety of differing R groups on both the carbonyl compound and the phosphonium ylide, and depending on the nature of these R groups, E or Z stereochemistry of the product alkene can be somewhat controlled in this reaction, and that's part of what you'll be observing in your analysis of the product in this lab. Like mentioned previously, the Wittig reaction uses the phosphonium ylide as a reactant. Ylides are compounds that overall are neutrally charged but contain two atoms that are oppositely charged and are adjacent to one another. The photo on the right is an example of a generic phosphonium ylide and two resonance contributors for that compound. The top image shows the ylide with the opposite charged atoms that are adjacent to one another. You can see the positive charge on the phosphorus and the negative charge on the carbon. In the experiment we're doing today, we have to prepare the ylide in situ using sodium ethoxide as a strong base. We start out with this benzyl triphenyl phosphonium chloride salt that is then reacted with sodium ethoxide to produce the phosphonium ylide, ethanol, and sodium chloride. The ylide is then used immediately without further purification. This is the reaction mechanism for the remainder of the reaction we'll be doing in this experiment. We'll start at the top left and move to the right going down, and then to the bottom left step by step. What happens first is the negatively charged carbon in the ylide will attack the carbonyl carbon and cinnamaldehyde via a nucleophilic attack. This will produce the intermediate we see on the top right, where we have the positively charged phosphorus and the negatively charged oxygen. This intermediate will undergo a rearrangement via the lone pair on the oxygen, forming a bond with the positively charged phosphorus, forming the ring that we see in the bottom right. This formulated ring is unstable and quickly breaks down into the products we see, one of which is our desired product, the trans-trans 1,4-diphenyl 1,3-butadiene, and the cis-trans 1,4-diphenyl 1,3-butadiene, and the phosphine oxide, which is an incredibly strong phosphorus-oxygen double bond, which is part of the driving force of this reaction, and could also be considered a leading group in this case. Now we will go over a summarized procedure, starting with the preparation of the ylide. First, you'll add benzyl triphenylphosphonium chloride to a 50 milliliter dry round bottom flask. You'll then add absolute ethanol to the flask and allow it to stir. Lastly, you'll add sodium ethoxide solution to the flask and allow it to stir for 15 minutes. Observe and record any color changes that may occur over this 15-minute period. And now onto the synthesis of 1,4-diphenyl 1,3-butadiene. While you're allowing your sodium ethoxide solution to stir, add cinnamaldehyde and absolute ethanol to a test tube. Once you've done this, stopper the test tube until the ylide has stirred for 15 minutes. After the ylide has stirred for 15 minutes, add the cinnamaldehyde solution to the round bottom flask containing the ylide via a pipette and let it stir for 10 minutes. Make sure to observe and record any changes that may occur. Now we'll move on to separating out the trans-trans isomer from the cis-trans isomer and other impurities. After the solution has stirred for 10 minutes, cool it in an ice bath. You'll then filter out the solution using a Buchner funnel. If necessary, you can use small portions of cooled absolute ethanol to aid in the transfer of your crude product to the funnel. Leave the product on the funnel to allow it to dry. After it's done drying, you'll want to save the liquid filtrate and pour it into a beaker for analysis at a later step. You'll then place your crude product in a beaker Add water, and then you'll filter this product again using the beaker funnel to remove the remaining impurities, and then lastly, allow the product to dry. Lastly, we'll move on to the analysis of the product. You'll want to analyze both the product and filtrate from the previous step via thin layer chromatography. The procedure for this will be to dissolve a small amount of your product in acetone and spot it on the TLC plate. You'll then spot the filtrate on the TLC plate and develop the plate using petroleum ether as your developing solvent, and visualize the spots on the plate using a UV lamp. Make sure to note any results you see from the plate, such as presence of spots in both the product and filtrate and their respective RF values. After TLC, you'll determine the melting point of your solid product. If the melting point is below 145 degrees Celsius, you will need to recrystallize using 95% ethanol. Finally, determine the percent yield of your product.